So you can simply take a sound file and drag it and drop it into your patch, and then we connect it to a EZDAC tilde object, which turns into a little speaker icon that we can then connect the first two outlets of our sound file to the EZDAC. And mine's already on. Yours will be off when you create it. So just like a toggle, you click it to turn it on. And turn my volume down here and listen to our sound. Very nice. Okay. And we can take this sound and we can divide up its frequency spectrum using cross tilde, which is a type of filter that takes the sound and chops it into different frequency bands. It's like a hatchet that in this case will be chopping it at 200 hertz. So all the sound under 200 hertz is going to come out of the left outlet, and all the sound over 200 hertz will come out of the right outlet. So if we listen to it now, we're just going to hear the low frequency components of the sound. And in the beginning, there aren't any, or they're extremely, extremely low. But when the bass drops in, we'll hear that. Right, so that's all the components of the sound under 200 hertz. And we could listen to, for instance, all the components of the sound over 8,000 hertz, and that's going to give us the very, very high end of the sound. The high component comes out the right. And there's the high frequency components of the sound over 8,000 hertz. Now that's extremely high. For this example, we can try something more along the lines of 4,000 hertz. And we want to use this frequency sliced sound to drive our imagery. So let's take these sounds under 200 hertz and compute the average volume of those sounds, because we don't want to deal with the sound directly. The same information that's going to the speaker is not going to be useful to drive the imagery. But one analysis of it that is useful to drive the imagery is the average volume. So we use AVG tilde to calculate the average volume of the sound. And then you need to make one more connection to make this AVG tilde work that I'm not going to explain right now, just know that you need it. It's the middle outlet of the JIT.world to the left inlet of the AVG tilde, and it's computing the average volume of the sound. And we can see that becomes a numeric volume. So there's an object called the floating point number box that we create with the letter F that will show us as a number what that average volume is. This is a floating point number box, which is just a way of displaying numeric information. It just shows us that there's a number coming out. And of course, once we have it as a number, we can then take that number and apply it to something else, like, for instance, the size of our sphere. We can use $1, and that will just be replaced by whatever number we pass into the message box. And now our sphere is sound responsive. So we're chopping out all of the high frequencies. We're only using the low frequencies. We're calculating the average volume of the low frequencies, and then we're having the number that indicates the volume, that indicates the loudness of those low frequencies, mapping it directly to the scale of the sphere. So we can do the same thing with the high frequency sounds here. Let's make another sphere. And what I'm going to do is I'm just going to take this one, and I'm going to take this whole structure here. I'm going to draw a box around my average, my number box, my scale, and my JIT.gl.grid shape. I'm going to copy them and paste them. And now I have this second sphere, a blue one. And I'm going to calculate the average of the high frequency sounds. making the same connection from the middle outlet of the JIT.world into the average tilde. And the spheres are in the same place, so if I want to move this a half a meter to the right, I say 0.5 in the x dimension, 0 in the y dimension, 0 in the z dimension, and this will move the blue sphere to the right. And there we can see my blue sphere that's representing what's happening in the sound over 4,000 hertz. And we can listen to this with the whole sound. And we can see the two spheres are responding nicely to their different parts of the sound. The red sphere is responding to the bass, and the blue sphere is responding to the high frequency sounds. The one thing that's a little odd is the blue sphere is small. Why is that? Well, it's because these high frequency sounds are quieter than the low frequency sounds. If I want the blue sphere to be larger, I can do a couple of things. One, I can just take this average volume, and because it's a number, I can add to it. Well, let me delete this patch cord and create a new object that has a plus sign in it, and that will add some value to the average volume of the high frequencies of the sound. I'm going to add 0.5 to this average volume, and let's see what that does in terms of scale. It starts my blue sphere pretty big. So we can see that the blue sphere is responding, but it's still responding in a slight way. It's just starting bigger. And that's what addition is going to do for us in this case, is it's going to calculate this average volume and then add a fixed value to it. So the sphere itself will get bigger, but the changes will remain the same size. So another thing we can do is multiply. We could take this volume and let's say we multiply it by 2, doubling it. And notice I put a decimal point after the 2 because I want floating point arithmetic here. I want it to include fractions. And let's see what that does. So we can try and change this. We can say, let's say, what if we multiply it by 4, make it more extreme. So now our loudest blue sounds are going to make the blue circle 4 times as large. See, it gets quite large there, as they would have if we didn't do any multiplication. We're just making the average volume have 4 times greater effect on the scale of the blue sphere.